Hello everyone, in this video we are going to visualize the magnetic field using the geometry nodes in Blender 4.5. This is really amazing fact. First I'll go through the concept of this and then we're going to build the node tree for the tracer, and after that we're going to add the magnetic field calculations in that. Then I'll show you how to add a nice material to this for the rendering. So let's get started. Suppose we have this wire, so it is carrying some current and we want to calculate the magnetic field at this point. Okay, and to calculate the magnetic field we have this formula, that is Biot-Savart's law. With this formula we can calculate the magnetic field. So in this formula we have this constant mu naught over 4 pi, and then we have this integration over current, the current that is carried by this wire, times dl vector. So dl is the smallest length segment of this wire, time r cap. R cap is basically the unit vector of this distance vector divided by the magnitude of this distance vector. If we plug all these things and do the integration, we can calculate the magnetic field. So for our purpose, we're going to first simplify this formula. So we have this. So first we're going to treat this constant as some factor. And suppose our wire is carrying a constant current, so we can take out this current from the integration and merge that with the S factor. And in the next thing is that if our segments, this DL segments have constant magnitude, so we can also merge that into S. Then we only need to calculate on this DL cap, basically the unit vector that is pointing in the direction of the wire. Okay, so now we have this really simple formula. So we need to calculate DL unit vector and distance unit vector divided by the magnitude. Then we can multiply this by some factor. Okay, so next we need to do the integration. To do this integration numerically, we need to break that into summation. So basically we need to divide this wire into small segments and then calculate the magnetic field from each segment and add them together. So that will provide the total magnetic field at this point from this wire. Okay, so if you keep this DL small for the summation, you will get a better and more accurate result. So that's why we have different kind of integration methods for more accuracy. For our case, we're going to use Euler method and we're going to keep this DL small. Okay, so this is the concept, and now let's build the tracer. So first we're going to add a plane and then we're going to add the geometry node setup. Okay, so first we need the points. Okay, let me delete this because we're going to use our own geometry, so that later you can easily replace that for different geometry. So we have this mesh and then we're going to distribute some points on that. So we have these points. So here I'm going to briefly explain the steps for the tracer. However, if you want in-depth explanation, please check out this video visualizing the electric field with the geometry nodes. Okay, in that I cover each step in details. So we have these points. Next we need to store two attributes. Okay, the first one is going to be the index of these points, so that later we can separate them for the curve. And here we're going to store the Boolean flag. So let's call this P active. So this is really important when we want to separate the active points from the last iteration step. Okay, and after that you can also add another one that is mainly for the material. We can add the P random random attributes per points. Let me add the random node. So now we have some random information on the points so that we can use that in the material. So next we need the repeat zone node. So here first we're going to separate the active points. So let me add the named attribute node and then add this P active flag that we have stored here. So next we're going to add the set position node. So we're going to add some offset to these points, and after that we're going to join them with the original points. And here we need to do one more step. Basically we have to deactivate these points after the separation. So now we have this tracer, and let me show you this. If I do the offset along the x-axis and increase the iterations, see we are tracing these points. We can also do that probably in the z-axis. See? So next we can convert these points into curves. So let me add the points to curves node and it connect all these points, but we want to connect them based on this ID, and that ID is going to be the P index. Now let me add that here and type the P index. See, now we have these curves that we are tracing. So this is our tracer. Okay. Next we're going to introduce the calculations based on the magnetic field. So basically we're going to offset these points based on the magnetic field. So for that we need to introduce the wire. Okay. Let me go to the top mode and add this Bezier circle. So why we are using this Bezier curve or Bezier circle, that is really important. Let me show you this. To do this integration, we need two things. One is dl vector and another is the distance vector. The distance vector is really easy to calculate from this point to this point. So we have this. For the dl, we need some vector that is pointing in the wire direction. So we can use this Bezier curve because it has tangent. So we can use that tangent vector as the dl vector. That's why we are using this Bezier circle as wire. Okay. We have this, and let me put this circle in a new collection called the current source. Later we're going to have multiple circles to represent different current sources. Okay, so let's add that here, make it relative. Let me zoom that. Then I realize this, because these are the instances, we need a real geometry. After that we're going to resample them, maybe around 50 points, or you can also sample that based on the length if we have different size of these circles, so that will provide a uniform length segment. I think let's do that. Okay, maybe let's say 0.25. Okay, so next we need to calculate the distance vector. Okay, so next we need the position of all these points for each segment of the curve. So for that we're going to use the duplication method. However, I have also explored different kind of methods for the integration. So if you want to study them, you can get the project file from my Patreon page. For the duplication method, first we need to duplicate these curves. We want to duplicate the splines, and the amount should be equal to the number of points. Change that to points and plug that into the amount. So now we have same number of curves, and really nice about this node is that it also provides the duplicate index. Okay, so we can use that to sample the position for individual segments of all these points. So let me add the sample index node, change that to vector, and type here position, because we want to get the position, and here we can use duplicate index to get the position for individual this duplicated curves. Okay, so let me show you that. If I plug that here, so we have these curves, and so we have these positions. So now you can see that one point has one curve, so we can easily calculate the magnetic field and do the summation on that curve, and after that we're going to transfer that data back to the point. Okay, so we have this position, and next we going to add the subtract node and plug that into this, so that will provide the distance vector. And after that we need to normalize this, because we need the r cap vector. So this is the r cap, and also we need the length or the magnitude of this distance vector for the formula. Now we have the r cap and we have this distance r, and let me also add the power, and the power should be -2, because this was at the denominator. Okay, let me show you that. This is at the bottom. Okay, so next we need the dl vector or the tangent of these curves. So let me add the curve tangent node. We have that. Then we need to cross product this with this r cap. Okay, and because we have already used -2, so we can directly use the v scale to scale this vector, or it is simply like we are multiplying this by this. Okay, so Now we have this. Let me also bring that here. So next we have this magnetic field for all the points based on the individual segments. Okay, so we need to do the summation. So for that we're going to use the accumulate node. So we have this accumulate node, it provides the total magnetic field. So then we need to define the group ID, and here we can use the duplicate index. Why? Because we have one curve for one point and we want to do the summation for all the segments of the curve for that point. Okay, if we want to calculate the magnetic field for this point from this circle, so we need to calculate the magnetic field for all the segment of this curve and then do the summation on this curve. That will be the total magnetic field for this point. So based on this circular current loop. So now we have this total magnetic field for all the points based on the segments of the curve. Okay, so next we need to transfer this magnetic field to the point. Okay, so we're going to use the sample index node and plug that into the value and connect this to the geometry. Because we are sampling from the spline, so we're going to change that to the spline, and here we can input the normal index. Why? Because we have one curve for one point. So let's plug that into the offset. And for more control, first we can normalize this because we are only interested in the direction of the magnetic field. And then we can add the V scale, vector scale node, so that we can control the length step or the integration step. So for better accuracy. So we have this. Now let me increase the number of iterations. So 150, and let's also increase the points. See? So now we have these magnetic field lines based on this circular current source. And you may notice that they are not closed loops. This is because our integration method is really simple. It is a basic Euler method. So that's why they are not closed loops. However, if you decrease the length step and increase the number of iterations, you get really accurate and almost closed loops. Okay. So, but in this case, we are only interested in the visualization, not for that scientific accuracy, but it is possible to calculate this accurate magnetic field. Okay. Let me make this around 35 and let's decrease the number of iterations and let's add multiple current sources. So we have this curve, and let me scale that down. So we have something like that. We can even duplicate that. So maybe slightly move that in the Z direction. Here it is not limited to this grid. You can input any mesh, maybe icosphere. We have these points and then we have these lines. You can even increase the size of this icosphere. So we have this, and let me decrease the size. Okay, and also decrease the density. So next we're going to add the nice material to this. So let me first show you the complete node setup. Okay, so this is our node setup. So here we're going to add the C to mesh node, curve to mesh node, and then we're going to add the curve circle for the profile, maybe 0.075, yeah, something like that. And after that we can add the set material node, and let me add the material to this. Okay, so the one way to add nice variation, we can add the attribute node, then type p random that we have stored for the points. See, we have this random information, so we can add a color ramp node, plug that into this, and here we can add really nice color to this. Okay, something like that, maybe slightly warmer, something. So in my case, I use 0.35 and also use the transmission weight 1 and use the cycles. Maybe slightly higher. I think 0.4, even 0.5. Yeah, something like that. And another thing is that suppose you want to visualize the magnetic field direction. Okay, so you can also do that. First, we need to store the magnetic field and the points. Change that to vector, and we can store this. So this is P underscore field. Then we can use that here. Named attribute node type P field. So it is same, but now we have the information about the magnetic field. Let me add the name attribute node P field. Now we have this. Let me hide the text. See, we have this information about the direction of the magnetic field. So we have this. Now you can easily separate the direction. Let me add the dot product with the z-axis. So it will provide the information about that. So we can use this P magnetic field in the material. So let's duplicate that. Type here P field. So we have this, and next we can normalize this. After that, we can add the dot product with the z-axis. So we have this. Next, we can also add the map range node because dot product can be negative. Okay. And then we can plug that into this. So now we have this is with random and this is with this magnetic field direction. So even you can also add some variation to this. You can plug that here and add the hue saturation node and use this for the hue. So this is the material setup. So this is how you can add the variation in the material, and this is the complete node setup for this. This is it. You can get all the project files from my Patreon page. So I hope you learned something from this video. So if you like, then please like the video and subscribe to my channel for more updates. So thank you for watching. See you in the next video. Happy noding. Bye.